Assalamu alaikum. Welcome to the next lecture. Uh, in this lecture, we'll be discussing the ideal transformer. It's very important to discuss the ideal transformer because the practical transformer has a close appearance to the ideal transformer. So, and sometimes we almost always we can say that we represent the transformer by ideal transform. But we should know it is practical limitations or we can say constraints. So before doing that, we'll first discuss the ideal transformer. So in order to visualize the effect of the flow of secondary current, because until now we haven't discussed the effect of the secondary current, we make certain assumptions which are definitely very close approximation for the practical transformer. So a transform possessing these ideal properties is hypothetical. There is no real existence of that. Uh, when we consider this hypothetical properties of a transformer, we'll refer this type of transformer as ideal transformer. So the assumptions are that the primary and the secondary winding have zero resistance. It means that there will be no ohmic losses or there will be no copper losses. There will be no resistive voltage drop in this ideal transformer. But in an actual transformer, it has a finite but small winding resistance. It will also be assumed that there will be no straight capacitance, though the actual transformer has inter-turn capacitance and capacitance between turns and ground. But the effect is negligible at 50 Hz because capacitance, capacitive reactance or capacitive admittance will come is dependent on the frequency, and at 50 Hz it is negligible. So we can neglect them as well in practical transformer as well. Since in the previous lectures we discussed about the leakage flux, here we assume that there is no leakage flux, so that all the flux is confined to the core and it links both the windings. An actual transformer does have some amount of leakage flux which can be accounted for in detail analysis by appropriate circuit modeling. So actually we are taking that into consideration when we discuss about the transformer. The core has infinite permeability, so that zero magnetizing current is needed to establish the requisite amount of flux in the core. Since we know that the flux is dependent on the voltage and the frequency, and this flux is related to this exciting current, that is mmf, which is equal to Ni is equal to phi into reluctance. Since permeability is infinite, reluctance will be zero. When reluctance is zero, phi into zero will be equal to zero. That means for any amount of flux that is to be established in the core, no current will be needed because the reluctance offered by the core will be zero in this case when we assume infinite permeability. One more thing, the core loss, that's hysteresis, as well as eddy current loss are considered to be zero. So these are the four important assumptions that we made for a transformer to be an ideal transformer. So let us now discuss about the effect of the secondary current. We will assume that we have a transformer of primary turns of N1 and secondary turns of N2, which are wound on a common magnetic core. The voltage source is connected to the primary side and its value is root 2 V1 cos of omega t, while this V1 will be now RMS value of this voltage. First, we'll assume that the secondary is initially open. So as a consequence, the flux is established. So flux is established over here, and which is determined by this equation. That means this V1 or this E1, they will be same because we are assuming there will be no winding resistance of this copper winding. So the flux and voltage are related by this equation. So, but the exciting current drawn by the source is zero, since we assume that infinite permeability. The flux, which is wholly mutual, that is, there will be no leakage flux. Whatever flux will be here, that is linking to this winding as a whole, causes the EMF E2 to be equal to N2 d phi by dt. That will induce the voltage E2 in the secondary winding, whose polarity will be plus and minus. So I will discuss it again. How does this polarity comes out? So if this is connected like this, I2 will flow, and since I2 is shown, it is not yet clear what will be the direction of the I2. First, we have to be very much sure that this current will induce the voltage, sorry, this flux will induce the voltage in such a way so that it will produce the flux opposite to this flux. That means when flux is in this direction, when we keep our right hand thumb in this direction, and we put the fingers or curl the fingers around this winding, you will see the current direction will be this and this. That means current will flow like this. That's what it has shown over here. So you have to take care of that, and when the current flows like this will be positive, this will be negative, because this will be a source, this will act as a source of the power. And we know that the source of the power, when supplies the current, it supplies it from the positive source, and it returns from the positive terminal, and returns from the negative terminal. So this is what is meant by the this dot one. And I told you that if this is the positive polarity over here, this will be the positive polarity over here, because their polarity will be same and they are marked as dot. And dot polarity marking means whenever the current enters at the first dot, the current leaves at the second dot. And the same polarity due to the EMFs induced. That is what I have just described. So from the above two equations, E1 by E2 will be equal to N1 by E2, that is the transformer ratio. This will be the instantaneous value of the induced EMFs, because E1 uh, actually it should have been E1 will be equal to N1 d5 by dt. That means E1 by N1 will be equal to E2 by N1, E2 by N2, and you can rearrange them. E1 by E2 is equal to N1 by N2, that is equal to E. That's the transformer ratio. Since A is the transformer ratio, which is a constant, so E1 and E2 will be in phase. The secondary terminal voltage V2 will be equal to E2, because of there will be no resistance present in the circuit. Therefore, V1 by V2 will be equal to E1 by E2. That will be equal to N1 by N2. That's equal to E. That's the transformer ratio. In actual practice, there will be slight difference between V1 and E1 and V2 and E2. It is therefore seen that an ideal transformer changes the voltage in direct ratio of the number of turns in two windings. It's very important. So what does this mean? It means V1 by V2 is equal to N1 by N2. It changes the voltage in the direct ratio of the transformer ratio. So in terms of RMS values, it implies this capital V1 by V2 is equal to E1 by E2 is equal to N1 by N2 is equal to the transformer ratio. Now let us connect. This is very important. You need to be very careful here and very attentive here. Now let us connect the secondary load impedance Z2, that is like this, so that the secondary feeds a sinusoidal current to the instantaneous sinusoidal current of instantaneous value I2. We can say that I2 starts flowing when we connect this I2, because induced EMF is present here. Due to this, the flow of current, the secondary creates F2, that is the MMF produced by the winding 2, which is equal to N2I2, that opposes the flux. That I just told you, that whenever the current flows over here, it produces the flux in such a way so that it opposes it. When current flows here, you will see that this flux will be reduced. When this flux reduces, you will see that this flux reduces. But as I have told you in the earlier classes, that the transformer is a constant flux machine, and it may, if this happens, it may make the imbalance in this V1 and E1, and I will told that also how does that happen. When this flux decreases, so to maintain this flux constant, this transformer will draw, because when this flux reduces, this E1 will also reduce. When E1 reduces, V1 is constant by the source, this current will increase, because there will be now the imbalance in the voltage. When this current increases, the flux, or we can say the MMF here, also increases. So when this current increases, the MMF increases. This current increases in such a way so that this MMF, that is N1 and I1, will be equal to this N2 and I2, because we are assuming there will be no exciting current. There will be only current that is balancing this current. Because I will repeat again, when this current increases, the MMF produced by this winding, that is N2 I2, will produce a flux which will be opposing to this flux. This flux reduces, which reduces this flux. When this flux reduces, there will be imbalance between V1 and E1. I1 will increase. I1 will increase in such a way so that it increases the flux. Again, to it is the constant value which is determined by V, this V1, and it is frequency. So in that case, this flux remains again constant. That is why I told you in the previous classes that transformer is a constant flux machine, and it is independent of the load current, because when load current increases, so to balance that flux of the machine, it draws the current from the primary to make this flux again the same value as that of the previous value. So this is very important. However, the mutual flux it cannot change, as I have told you. Otherwise, V1 and E1 balance will be disturbed, because for the time which we have assumed for the open circuit secondary, this V1 and E1 will be same, because there is no winding resistance. Now, because of the increase in the secondary current, flux reduces, E1 decreases, V1 and E1 will disturb, and there will be the more current. The result is the primary draws the current I1 from the source, so as to create MMF F1 is equal to N1 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 I1, which at all the time cancel out the load caused load caused MMF N2 I2, and the phi flux is maintained constant independent of load. Therefore, I1 N1 will be equal to I2 N2. That means I1 by I2 will be equal to N2 by N1, which is equal to 1 by A. This is the current related to this term ratio. Obviously, I1 and I2 are in phase, because this is again constant. And for a positive directions marked on the diagram, for this direction of the diagram which we have calculated by the Lenz's law, primary current into the dotted terminal and secondary current out of the dotted terminal. Since flux is independent of load current, so E2 and V2 must always be equal to E2. So both will be equal to E2. They will not change, because E2 will now increase when flux increases. So the secondary is also resistance less, this V2 and E2, because in this case we are assuming there is no resistance. So therefore, from the equations, I write down the equations again. I1 by I2 is equal to N2 by N1 is equal to V2 by V1. So this is the total relationship of the current, turns, and the voltage. So when you multiply them like this is N1 by N into N2 is equal to, sorry, when you multiply this and this is I1 V1 is equal to I2 V2. So which means that instantaneous power into the primary equals the instantaneous power out of the secondary. So this is also the consequence, or we can say the assumption that we have made, the first assumption, that the transformer is power. Transformer does not consume any power. This is actually the consequence of the assumption first and fourth. In first, we assume a resistance is zero, there will be no copper losses. In the last one, we assume core losses is zero, which is also active power loss. So in that case, this result is very relevant. In the RMS values, this can be written as capital I1 by I2 and 2 by N1 is equal to 1 by A, which implies that the current in an ideal transformer is in inverse ratio of the winding turn. Voltage was in the direct ratio and current is in the inverse ratio of the winding turns. The kVA in terms of RMS value will be equal to V1 I1 is equal to V2 I2. That is, VA output is balanced by the input VA. So what will be the VA in the input, same will be the VA in the output. So you need to be very clear about this. This power remains unaltered in case of the transformer. It will not change. It has already seen above that the V1 and V2 are in phase, and so are I1 and I2. I1 and I2 are also in the phase. Now, writing the equations again, that's voltage and current equation in terms of the turns ratio. That is V1 by V2 is equal to N1 by N2, and I1 by N2, I2 is equal to N2 by I1. I will divide these two equations, that is V1 by V2 divided by I1 by I2 is equal to N1 by N2 divided by N2 by N1. So it will be like this. Now I will write them, since I will write them like this: V1 by V2, mm, V1 by V2, sorry, I will write it like this: V1 by I1 multiplied by I2 by V2. So I will take this I2 by V2 to this side, it will be equal to V2 by I2 into, then this will be equal to N1 by N2. When I take them to upwards, it will be again N1 by N2, it will be equal to N1 by N2 whole square. So the equation will become V1 by V2 is equal to V2 by V1 into N1 by N2 whole square. That is this: V1 by I1 is equal to N1 by N2 square into V2 by I2. From this, since we have assumed the transformer is connected, an impedance of Z2 on the secondary side, so this I2 will be equal to V2 divided by Z2. When this I2 will be equal to V2 divided by Z2, that means this Z2 will be equal to V2 by I2. So I can replace V2 by I2 by Z2, that is this impedance. Now the primary will supply a current I1, assuming that there is some impedance, that is Z1. So this I1 will be equal to V1 by Z1. So, or we can say this V1 by I1 will be equal to Z1. So we can assume that this Z1, that is impedance seen by the source V1, will be equal to N1 by N2 whole square Z2. That is this N1 by N2 whole square Z2, because this will be equal to Z1. So this is nothing but the turn ratio A, transformer ratio A, Z2. I can replace it by Z2 dash, where Z2 dash is equal to A square Z2. So we can say it is concluded that the impedance on the secondary side, when seen or referred to, sometimes we can say when the impedance seen by the primary, or when the impedance is referred to the primary, on the primary side of the transformer is in direct ratio of the square of the turns. So when I transfer this, or when I refer this impedance to the primary of the transformer, it is to be multiplied by the square of the turn ratio. Now you can see we have the equivalence of these equation by the transformer. So when we transfer it to this, or when we refer this, you can say when you refer this impedance to this side, it will be first transferred like this. So this Z1, that is the impedance seen by this, we can assume that the impedance offered by this will be 0 because of the assumptions of the ideal transformer. So this Z1 will be equal to N1 by N2 whole square into Z2. Now omitting this, after that we will be replacing, because this source has nothing to do with this. It is only supplying current based on this impedance, because the impedance of this will be equal to 0. So that V1 by I1, that is Z1, will be equal to N1 by N2 into Z2, N1 by N2 square into Z2, which is equal to Z2 dash. So Z2 dash will be like this. So similarly, an impedance of Z1 from the primary side can be referred to the secondary side. So in that case, that Z1 dash will be equal to actually 1 by E square Z1. So that will be referred like this: Z1 dash is equal to N2 by N1 whole square Z1, that is 1 by E square Z1. So in conclusion, transferring an impedance from one side of a transformer to other is known as referring the impedance to the other side. Voltage and current on other side have their counterparts. On one side has a counterparts, on the other side they are actually related to the counterparts by the transformer ratio. One will be the direct transformer ratio, another will be related by inverse transformer ratio. In conclusion, it may be said that an ideal transformer transferred are transformed in direct turn ratio. Ideal transformer voltages are transformed in the direct turn ratio of the turns. Currents are transformed in the inverse ratio of the turn, and impedance are transformed in the direct ratio squared. While, which is very important, power and VA, that's the real power, and VA, that is the apparent power, remains constant and unaltered. The impedance modifying property of the transformer can be exploited for the matching of the fixed impedance of the source for the purpose of maximum power transfer by interposing a transformer of suitable turn ratio between the two. As I told you in the earlier classes, for example, this is the source, it has some source resistance, and it has some we can say this load resistance. So since it is uh, it is referring it to primary as this resistance. There will be some resistance. We can alter the turn ratio in such a way so that this impedance will be made equal to the source resistance. In that case, we'll be able to transfer the maximum power to the uh, to the load. So this in this way we can exploit this property of the transformer to match the impedance so that we can transfer the maximum power. Now let us try to do some numericals and we will be uh, more comfortable in understanding this. Assume a transformer of figure this earlier figure to be an ideal transformer. This will be also an ideal transformer. The secondary is connected to a load of 5 angle of 30. Calculate the primary and secondary side impedances, current and their power factor, and the real powers. What will be the secondary terminal voltage? This is very simple. You can say the primary is supplied by a voltage of 200 volt and the turn ratio is 150 divided by 75, that is 2, and V2 and I2 are to be calculated, I1 is to be calculated, and Z2 is given as 5 angle 30. So Z2 is given as 5 angle 30, A, which is the term ratio, that is N1 by N2 is equal to 150 by 75, that is 2. Z1 can be calculated as Z2 dash, that will be equal to N1 divided by N2 whole square into this Z2, that will be equal to 2 square into 5 angle of 30, that is 20 at an angle of 30. From this Z1 we can calculate the value of this I1 because this I1 will be equal to 200 divided by this I1. So now you can also do it by other way. You can first calculate V2. V2 will be equal to this 200 divided by this 2, that will be equal to 100 volt, and this I2 will be equal to this 100 volt divided by 5 angle of 30, that is equal to 20 at an angle of 30 minus 30, that is this. So when I2 is calculated, I1 will be equal to this 20 divided by 2, that is the inverse ratio of the transformer ratio, transformer turns, that will be equal to 10 angle 30. I1 will be equal to I2 dash, that is 20 angle 30 divided by this should be minus 30, 2, that is equal to 10 at an angle of minus 30. So I1 will be equal to 10, I2 will be equal to 20, V2 will be equal to 100. Now the power factor will be cos of minus 30, that is cos of 30, that is equal to 0.866 lagging. Now we can calculate the input powers. We calculate the impedance, primary side impedance, secondary side impedance, primary side current, and this secondary side current. We can calculate the power factor. So primary side power factor will be, that is I1 will be 10 and at an angle of this 30, that is 0.86 lagging, and secondary side power factor will be again 0.86 lagging because the angle is again minus 30. Now we can calculate primary power, that is equal to 200 into this I1 into cos of theta. 200 into I1 is 10, that is 2000, cos of theta 30 will be root 3 by 2. It comes out to be 1732 watts, that is 1.732 kilowatts. You can also calculate it by doing this also because it will be equal to I square into R will be the real part of this impedance, that is 20 square, the real part of this, that is 5, cos of 30, that is 5 into root 3 by 2. You will calculate it, you will get the same value. Similarly, for this case you can also calculate it this way. I have shown it this way. Here you can calculate it V2 I2 into cos of 30. V2 is 100, I2 is 20, that is 2000, and to root 3 by 2, that will be again equal to this 1732 watts or 1.732 watts. So whether you use this formula or this formula, you can calculate in any ways. Here also, since in the primary it has used this VI cos of theta, so you can also use, that is I1 square into real part of this one, that is 20 cos of 30. You can get the value of the input power. So here also input power is constant, it will not change. Now let us try to do one more numerical. An ideal transformer has 3 windings, that is this 100 turns on the primary winding P, that is this, 160 turn on the secondary winding S, 160 turn on the secondary winding S, and 60 turn on the tertiary winding T. We have 60 turns on the tertiary winding T. Winding S feeds 10 amperes to the resistor load. We have 10 amperes to the resistor load, whereas a pure capacitance load across winding T takes 20 amperes. Here it supplies a 20 amperes to a capacitor. Calculate the current in the primary winding and its power factor in case of transformer magnetic current is neglected. Transformer is assumed here to be ideal. With the polarity marking on P as shown, mark the polarities on the windings S and P also. Since the polarity here is P, that is on the primary winding is plus and minus, that the current is going like this. So that means flux here will be in this direction, like this, clockwise direction. Now this will draw the current to oppose this flux, so that means the flux direction will be upwards. So when we point our thumb, right hand thumb upward, and the direction of the fingers will be like this, right? This, 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 and this, and this. That means this will be positive, this will be negative. Similarly, for this case, it has to produce the flux like this, up anti-clockwise direction. So when it does so, when we uh, put the finger in the right direction, and we'll see the direction of our fingers, it will be from, it will be like this, like this, like this, like this, like this. That means current will be leaving at this term, and this will be positive, and this will be negative. So in this way, we're done with the polarity markings, and I hope you have understood this. Now I will calculate the currents in the primary. So I will do it in two ways. First way, I will assume that there is not any tertiary winding. There is only the uh, secondary winding and the primary winding. So we know the current in the secondary winding. So the relationship of this and this will be equal to I2 by I1, or I1 by I2 is equal to N2 by N1. So I2 will be equal to N2 divided by N1 into I1. Sorry, into I2. So this I1 will be equal to N2, that is 160, divided by N1, that is 100, into 10, that is 160 divided by 100 into 10. It comes out to be 16 amperes. But you need to be very careful. This 16 amperes will be, it will be a phasor at an angle of what? At an angle of 0, because this is a resistive current. Now assume that there is no secondary winding, there is only tertiary winding. I can use again the same formula, that I1 will be equal to I2 into N2 divided by N1. So I2 is 20, N2 is 60 divided by 100. When you do it, that is 100 into 60, sorry, 100, uh, sorry, 60 into 20 divided by 100, it comes out to be 12 amperes. But since it's a capacitive current, it will be leading to the voltage by 90 degrees. So this voltage and this voltage will be in phase, and this voltage will be in phase. All the voltage will be phase, the current will be leading. So that means if this is the current, which will be equal to 16 amperes, and the 12 amperes will be leading to it by 90 degrees. That means total current in the primary will be equal to this 16 plus 12G. The total current will be the square root of 16 square plus 12 square, that will be equal to 20, and power factor will be equal to, that is R by Z, that is real part by the total magnitude, that is equal to 16 by 20, that is 0.8, and the current will be definitely, power factor will be leading. Now I will do it. This is one way of doing this. I hope you understood this, because the book has not shown it like this. I will try to do it by MMF balance. So the MMF that is created by this will be equal to 160 into 10, and the MMF created by this will be equal to 20 into 60. So again, here you need to be very sure that this MMF, let us say it is in this direction, having 0 angle, and this MMF will be having a positive direction of this. So it is shown over here. Applied voltage V1 and a mutual flux are shown in the figure, that is this. This is applied voltage, this is phi, isn't it? So we need to be very sure about all these things. So phasor diagram of this, EMFs induced in the winding S and T are indicated, that I have just discussed. This will be positive, this will be negative, because this will produce a flux upwards, and by having the flux upwards, when we curl the fingers over here, you will see that this will be positive, this will be negative. Similarly, for this case, this will be positive, this will be negative. Current I2 is equal to 10 ampere, and therefore the secondary winding EMF will be equal to N2 I2, that is 10 into 160, that is 1600 ampere turns. That is shown over here. You can see we have shown it in this direction. Since in the previous cases we have shown that this is V1, and phi 1 will be this lagging to this V1 by 90 degrees. So in that case, this will be like this. Okay. First thing, I will only show V1 and phi, because V1 phi will be cos of theta, sine of theta, and v1 will be cos of theta. So v1 will be leading to this by 90 degrees, so this will be v1 and phi. First you will just understand these two things. Likewise, the current I3, that is the current flowing through this I3, that is 20, and therefore the tertiary winding EMF is equal to N3 I3, must be leading to E3 by 90 degrees. So this F3, which is 1200 amperes, it must be leading to E3 by 90 degrees. That means to this, and E3 will be and E3 and E2. See, they will be in phase. When this is the case, wait a minute, I don't think it has shown the E2. E2 will be in this direction. E3 will also be in this direction. So F2 will be in this direction, but F3 will be in this direction because of the capacitance. It will be leading to this by 90 degrees. So as the load is pure capacitance, resultant of F2 and F3, that is this resultant of F2 and F3 will be given this, or it will be given this. When it is referred to primary, it will be F1, which is equal to square root of this 1200 square plus 1600 square, it will be equal to 2000 ampere turns. So 2000 ampere turns will be this. This will be also equal to this. So the current, this 2000 ampere turns must be supplied, that is ampere turn, from the primary. That means this 2000 ampere turns will be equal to N1 into I1. So since N1 is 100, that means I1 will be equal to 20 amperes. So the current that is supplied from the primary will be 20 amperes. And this way also we can find it out. And the power factor angle, that is the angle between V1 and I1, that will be this angle. It will be given by you can say cos of theta, that is F2 dash divided by F1. So F2 dash is nothing but this, that's 1600. This F1 is that we have calculated 2000. It comes out to be equal to 0.8. That will be leading. This current will be leading. Polarity mark we have already done. I think this is enough for today. Thank you.